What's up? Welcome back. In this episode, you'll see how to solve day 14 for the advent of code. This one is called Parabolic Reflector Dish. We're still making our way, trying to figure out how we can fix the environment with these elves. And now we find ourselves in a pile of rocks, or we have these panels that have a bunch of rocks on them, and we can control if we're going to tilt the panel forward or back or left or right. And our puzzle input is the status of the current rocks that are on the table or on the panel here. The pound signs represent cube-shaped rocks, and the O's represent round rocks. And we have a controller that can tilt the table north, south, east, or west. When we tilt it north, all of the round rocks will roll up to an edge or up to another rock or up to a cube-shaped rock, but it will not roll past a cube-shaped rock. So by tilting it north forever, then we end up with a result that looks like this. So what we need to do is figure out the total load on the north support beams, which is calculated based on how close the round rocks are to the north support beam. So if it's right on the beam, that's a 10. If it's one away, that's 9, 8, 7, 6. So it's like the distance from the beam tells us how much load is on it. What we want to do is grab our puzzle input, and we're going to make like one of those pegboard type situations where when you roll a bunch of stuff along the board, they may or may not get stuck on the pegs. So let's grab this. All right, let's drop this in here. We're going to say input is equal to this set of input here. And our grid is going to be just an array of arrays with each of those elements in it. So here we can say input.each line map chomp, and we'll grab out the characters and we'll p the grid just so that we know what we're working with. And if we look at main.rb, this is what we get back. Okay. Now what we want to do is roll all of the rocks in part 1. We want to roll them all north and then calculate the sum caused by all of the rounded rocks. So what I thought about was like we want to treat each column individually, and then ideally we can roll all the rocks in a certain direction. And if we look at the grid at 0.join, then this gives us like the first row at the top. And technically we want to work on the first column instead of the first row. So if we do grid.transpose, that will give us the first column. We have 2 round rocks and then a space and then a round rock and then a space and then a round rock and then 2 spaces and then a pound sign. And my first thought was, let's treat each of these columns individually and try to get all the round rocks rolled all the way to the left. So let's do that. First is we'll just create a method here called roll or something, and then this will take in a line or a row of rocks. And what we can do is say something like row.length -1 dot times do I. So we want to look at each pair of mouse rocks. If we have a dot on the left, we want to replace that with an O because we want the rock to roll into place. So if we see a dot on the left and a round rock on the right, then we want to swap them. So we'll say row at I plus 1 is equal to row at I plus 1 like this. And I think now if we run roll of this, we should see something. This wants to return row. Okay, let's just start with our row here, and we'll p row.join, and then we'll try one roll on the row and see what happens. Okay, so we had one move closer and another one move closer, but we still have the space in between. So what we need to do is say some check if swap, or swap here is going to be false, and then swap is equal to true. And at the end, if we swapped, we want to recursively call on it again. Otherwise, we'll return the row. Okay, so now we have completely rolled all of our round rocks to the left. That is great. Let's try it with another row here. Okay, that looks like it's working well. And we'll try it with two. Fantastic. Okay, so it even stopped, right? The rolling rocks stopped at the pound sign. So I think this is working as we expect to roll a certain row. Now let's write a method called tilt that's going to tilt the whole grid. And yeah, we'll just, for now, we'll say map over this and roll each of the rows. Let's actually go grid.each do row, and we'll put row.join, and then we'll print out a line, and then we'll tilt the whole grid. And maybe we'll just say grid is equal to the whole tilted grid. And then we'll do the same print statement. And let's take a look. Okay, so we have our whole grid, and then we tilted, and they all slid to the left, right? We had all of the rocks, they all rolled to the west. They all rolled to the west. So technically what we want to do is we want it to tilt north. And so the way that we can do that is by transposing the grid and then transposing back. Let's see if we get the right answer here. Nice. Okay. So now we are rolling up to the top. So that's like roll north, basically. So technically, if we pass in a grid that is transposed, tilt it, and then transpose it back, we get back the concept of rolling north. So now we're able to tilt to the north. And the next part of the problem for part one is we want to calculate the total load on the north support platform. So we need to go through each of our rows and sum up the impact of a round rock being at the top. So let's make a new method here called weight. That's going to take in the grid, and we'll have to go grid each with index do row, and then row.each with index do cell. And if the cell is a 0, then we want some answer to be incremented. So here we can say answer plus equals, and the amount that we're increasing by is the length of the grid minus I, because if we're at the top, if we're at the 0th point, we want this value to be 10, which is going to be the length of the grid minus 0, since there's 10 elements here. So this should be grid.length minus I, and I think that might give us a weight. Let's get our tilted grid, and let's print out the weight for the new grid. Okay, we run this and we get back 136, which is the same answer as the part one example. So now we'll grab our own puzzle input here. Wow, that is a big grid. Okay, so we'll put that at the end as always. And then here, instead of input, we'll make input be data.read and run this again. We got this 113424. What does that look like? That is the puzzle answer for part one. Okay, awesome. So we are now able to calculate the weight on the northern support beams when we've tilted north one time. Part two, the parabolic reflector dish deforms but may not be able to focus the beam. All right, so for part two, the idea is that we can click another button in this control panel called spin cycle. And instead of just tilting north, it will tilt north, then west, then south, then east. And that is one cycle. And after the end of one cycle of the example input, it will end up looking like this. So what we need to do, the first thing we want to do is figure out how to make this cycle method. And then at the end, the question here is, after a billion cycles or something, what is the total load on the north support? So we're going to have to figure out how to make that work with less than a billion, right? But for now, we can just create a new method called cycle. Let's actually move weight up here. That will not change our concept of what a weight is. And yeah, let's make a new method here called like north, and that's going to take in the grid. And right now we already have this north method figured out, right? It's tilt the grid dot transpose. That will shoot us north. And we can keep that as part of our part 1 input. And maybe we can say part 1 is that. And let's actually comment this out for now. Comment out part 1 down here. Okay, so we want to go something like this, north, and then look what it, see what it looks like. And let's also, now we can, because we have a method that will tilt north, we can remove the transpose. But I do want to make sure that we're not modifying the underlying grid. So let's create a new north grid, and then we'll go through each of those and print them out. So if we look at our puzzle input for the example, we can see north, and then we want to do that for each of these cardinal directions. So we'll have north, south, east, and west. And then we'll have each of these north, south, east, and west. Okay, but if we run it, they're not actually going in different directions, right? Our methods for south, east, and west are going to be, they're all going to be a little bit different. In order to go east, I think that's actually the default. So if we just run tilt on the entire grid, I believe that should get us east. East, oh no, that's, okay, the default is west. Let's run it against west. Okay, west is working. East, in order to get a single row to tilt east, we want to roll each of the rows in reverse. So we actually want to like map, we want to map over each of the rows and call reverse on it, pass that into tilt, and then whatever we get back, we'll reverse that. We're going to rewind it. So that's going to get us east. So now east, we're rolling to the right. And then south, in order to go south, what we want to do is we want to reverse the entire grid, I think. Let's see. South, nope, that didn't work. We might need to also transpose. And then transpose back, and then reverse back. And cool, that gets us south. So now we have north, south, east, and west. Let's make a cycle method. And that's going to take in a grid. And the cycle is in a particular order here. So we need to go north, then west, then south, then east. North, west, south, east. North, and then west, then south, then east. Okay, that's good. It looks funny. All right, so that should be a single cycle. So if we run, put cycle, and we grab out our new grid, and then we print it out, what does that look like? Okay, so after one cycle, it looks like this. Let's compare that against the input here. So cycle should have, a pound sign at the top. We have this pattern of 3 at the bottom, and oh, we're missing one of these, right? So after one cycle, we expect this to have 4 elements in it. So are we like losing, are we trimming something off somewhere? All right, let's break these up so that we can take a look. Grid is equal to north of grid. Grid is equal to south grid. East, north, west, south, then east. All right, and we're gonna dupe it just so that we have a duplicate copy. I am not convinced that this after cycle 1 is correct, because it seems like our input is actually smaller or something. I wonder if we have a different, maybe we have a different input. What's going on? How could there be, So after one cycle, it should look like this. Let's look again here. Oh, you know what? The grid that we're passing in was already modified, maybe? Let's see. Yeah, let's make this so that it always dupes the roll. Okay, there we go. Yeah, it keeps it was overriding something that was being passed down. Okay, so now we have a cycle 1 that matches what it looks like in the instructions. Now let's run it a couple of different cycles. So maybe we do, I don't know, 3 times do n, and then we'll print out, oh, this is cycle n, and we'll keep going. Okay, so after cycle 2, or after 2 cycles here, it should look like this, which lines up with what we're seeing in the example. And then after 3 cycles, it should look like this, which it does. So the process should work if you leave it running long enough, but you're worried about the north support beams. So if we run this for 300 times, let's just take a look and see. You'll notice that cycle 298 and 299 are actually different. So 298 has this group of 3 round rocks here in the corner, and on this one, it has them all at the bottom. They're not necessarily going to just settle, right? So if you look really closely at this, they're not settling at all. When I initially was looking at this, I thought, oh, we can just, instead of running it 1,000,000 times, we'll just run it until it settles, and then we'll count the weight. But instead, this whole cycle situation is our hint that we have to look for cycles in our loop. Every time we cycle, we are going to get back a grid that is somewhat unique, right? And the thought is, let's go through a cycle, go through a cycle, go through a cycle, and just look at the data here. So let's print out the weight of the grid and the current cycle that we're on, basically, so that, yeah, this n is going to be representing the number, or like the cycle that we're on. We'll comment all these out, and this one. And okay, so for cycle 299, our weight is 64. For 298, it's 65. 297, it's 69. 69, 68, 63, 65, 64 again. So then we have 65. Let's actually just take out the printing of the grid so that we can see just the weights and the cycle numbers. If we look at the beginning, when we first started running through these weights, like the first couple cycles, it's not actually impacting, or yeah, for the at the end of the first cycle, nothing has really settled. There's still a bunch of weight on the north beam. But then after one more cycle, we're getting a lower number here, 69. Then after 2 cycles, we're getting lower. After 4 cycles, we're at 65. At 5 cycles, we're at 64. 7, we get to 63. And then ultimately, it like settles down, right, between 69 and 64. And somewhere in this process, there is a loop. It's going to go, at the beginning, it starts off traveling along some line of states that we are only going to actually encounter one time in the very beginning. And then we enter a loop where we're going to see the same states over and over and over. And so what we want to do is kind of like detect the cycle and the length of the cycle. And we also need to detect how long was that first section before we got to the loop. The way that I thought about doing this was I'm going to serialize the grid into a key that we can use into a counter dictionary, and we'll just count how many times we've seen that same grid pattern. And that'll let us see, we'll count up the ones that we only saw one time, and then for the ones that were more than that, we can figure out what the cycle length is. Let's see here. So we want to have some pattern counter thing that's going to be one of these counter cache dictionary things. Okay. And what we want to say is pattern counter at grid plus equals 1. But instead of pointing directly at the grid, I want to serialize that into a string so that when later on I'm duping this grid, because it's going to be a pointer to an array that has like different subarrays and things, I I want this to just always work. And I think I can say, so if we have an array of 1, 2, 3, and we do a.join, yeah, okay, so that should be fine. So grid.join can be our key into the pointer. So we'll say grid.join, here is our key. And then we also maybe want another visited, and this can be a set. And this will just be like if we visited it or not, and we want to know how many unique patterns there are. So this we can do visited, and we'll shovel in the key, and we should just get like a unique count. So now at the end here, if we print out pattern counter, it's going to be gnarly because our keys are going to be huge, but maybe dot values. We'll just look at the values for a second. And then we'll also print out the size of visited and see what we get here. Okay. All right, so puts pattern counter, and we'll put visited.length. So the total visited, like the total unique patterns here was 9. And then our pattern counter values, we got 1, 1, and then 43, 43, 43, 43, 42, 42. Yeah. I think what we can do is remove the values that are 1, that we only saw one time, and that will be kind of like the start of the, or like the length of the offset. So we can actually probably just do count ones, and this is going to give us our offset. And then our visited length is that, and then our cycle length is, or like the length of the loop is going to be visited minus offset. And then, yeah, so let's print all this stuff out and just see what we get. Okay, so this is telling us that our offset is 2 and our cycle length is 7 for the example input. And then what we want to do is we want to figure out what the weight is after the spin cycle runs for 1 billion cycles. Run cycles is going to be 1 billion. So in order to figure out our offset, we want to take the run cycles minus the offset. So run cycles minus the offset. And that's going to give us like the starting point of the first, or that's going to give us the number of cycles where we're inside the loop. And this is going to be some big number. It's not going to be, yeah, okay, so it's 1 billion minus the offset, which is 2. So it's still a massive number. Now what we want to do is take that number and modulo with the cycle length. And that is going to give us 4. Now we should be able to use 4 to index into our, to index in and grab out the weight, but we don't have anything that's really actually tracking the weight. We're just printing it out right now. So let's do another thing, weights, which is going to be a dictionary here, and we'll have our weights at n be equal to the weight of the grid. And really we only care about the first few, and after that it doesn't really matter. So now this is going to be like our index, and now we should be able to say puts the answer is weights at index, and let's see what we get back. Answer is 65. Okay, so we have an off by 1 somewhere, I think, because this is supposed to be 64. Okay, so the run cycles minus the offset, technically, if we want to run 1 billion cycles and the loop, like the start of the loop is 2, we also, I think, need a set for the initial, like the first run through this cycle, because we're executing the cycle on the grid before we start counting. So let's add another 1 here, and I think, oh, 69. Okay, so +1. Now we're just taking stabs here. All right, we get 64, which is the answer for the example input. Let's try it against our own input. I know we don't want to just mess around there, but it should work okay. All right, let's grab our grid and run it. Ooh, it's taking a second. Uh-oh. Okay. Ruby main.rb. All right, it's cooking. It's cooking. So we are running through a bunch of cycles. Do we actually need to run through all those cycles? Probably not. So let's open this up and let's decrease our cycle length to 200 and just see if we can get away with something. Let's also run it this. Okay, we finished 99 sort of test cycles. It says our offset is 102 and our cycle length is 9 again. So we get 102, 569. And our puzzle answer was 96003. So something is wrong. Something is wrong here. Let's take a look. What is going on? So let's take a closer look at the values of this counter, the pattern counter. So let's like take this from the very beginning. So we'll p pattern counter dot values, and let's use the example input to start just so we can get a better idea of what's going on here. So we've encountered this first and second pattern twice. And then we have 1, 2, 3, 4, 5, 6, 7 is our cycle length, and 2 is our offset. I thought that maybe we can actually do partition, or yeah, let's just do count. Yeah, if we count up 1, or maybe it needs to be like, yeah, count ones. That should give us the number, and then our cycle length should be pattern counter dot values dot count, where it's greater than 1. Is that the same as what we had before? So cycle is 2, offset is, or cycle is 7, offset is, okay. And then we have our run cycles, and the index into weights is the number of run cycles minus the offset. So that's -2 plus 1. So that'd be 99. Actually, this must be minus. This has got to be minus. Okay, and if we run that, we get 69, which is not the right answer for this one. I am starting to think that our key into our weights is wrong or something. Do we need to dupe this again? Shouldn't have to. 69, okay. If our offset is 2 and our cycle length is 7, -2 modulo 7 is 4. And our pattern values, p pattern, our weights at n, or actually just p the weights. So 0 is 87, 1 is 69, 2 is 69, 3, 4, 5 is 64. Oh, okay. So we need to index at the offset plus the index, right? Because yeah, we don't want to use 3 as our index. We want to use 5 as our index, and in order to get from 3 to 5, we need to skip over the offset. So the offset was the first 2, and then yeah, that makes sense. Okay. Ooh. All right. So let's try this against our actual input. And all right, 96003. And that is our puzzle input for part 2. Awesome. Okay. Whew. That was another tough one. I don't think we actually need this visited thing anymore. I think we can get away without it. And then I'm also not sure. Yeah, I feel like we do still need this different key into weights. We want to collect up the weights just as we are. We could make this more efficient. Instead of just blindly going 200 times, we could say, oh, as soon as pattern counter at key is greater than, yeah, so I guess we could say break if pattern counter at key is greater than 2 or something, just to be safe. And that should go much faster, I think. Maybe. Okay, it's a little faster. We only ended up going through 120 cycles that time, and we still got the correct answer at the end. So that is cool. For more videos about Ruby, stick around by hitting that subscribe button. Thank you so much for watching. Really appreciate your time and attention, and we'll see you in the next one. Cheers.